Hello, students. We're going to continue on in chapter 21.3. We were talking about coordination compounds. So here's a compound. And I know that looks very daunting, but it would be the equivalent of looking at something like calcium chloride. I know it doesn't seem like it, but if you notice the calcium is a 2 plus and there's 2 chlorides to balance out the charge. That's the same in this compound. What's in bracket is our complex ion. And it's forming a salt with chloride. And then overall, the whole thing is a coordination compound. Now let's identify what has to be true in that ion is that since there's 2 chlorides, the charge on this whole thing has to be a 2 plus. Just like calcium ion is 2 plus here with the one negative for the chloride, and there has to be 2 of them to balance it out. Okay, so other concepts here is that the metal is in the center, and then it's a Lewis acid electron acceptor, and then the ligands are the Lewis base electron donors. Now our ligands, some are neutral, some have charge. So the famous ones I've been focusing on are water as a ligand, ammonia as a ligand. Those are neutral. So there's 5 of them, but that doesn't provide any charge here. The Cl is Cl minus, just like it normally is. So that's a 1 minus. So now the question is, what's the charge on the cobalt? So that this overall complex ion has a charge of 2 plus. And if you think about it, then it has to be a 3 plus, right? This 3 plus and a negative 1 give us an overall 2 plus. Okay, so what we want to picture then is there's the cobalt 3 in the center. And then there's 5 ammonias and 1 chloride. And through the lone pairs on those, they create a bond with the metal. And in this case, the coordination number is 6 because there's 6 things around the cobalt 3. Okay, and then the other thing that we talked about in the previous video is how we come up with how many d electrons that cobalt has. So normal cobalt, and I just grabbed my periodic table, is argon 4s2, 3d7. Let me make sure I'm going to count it. 1, 2, 3, 4, 5, 6, 7 going across the D's. So if it's a 3 plus, remember, always loses the 4s first in one of these. So our cobalt 3 plus is a D6. And then once again, that's our Lewis acid electron acceptor. And these guys are, the ligands are the Lewis base electron donor. Okay, so I just want to show you how they're named. It might create a little stress at first, but you shouldn't panic. Number 1, I usually pick easy ones. And number 2, on a multiple choice, they're easy to spot. It's a little bit different when you have to just write them out without any hint from a multiple choice question. So I think you'll be fine. Most students, this is like freebie points on the test. Okay, so what we do to name them is we have to figure out what the ligands' names are, how many there are. And so in this case, there's 5 ammonias, which are called amine. And there's 1 chloride ion, which is chloro. So if I have 2 different ones as the ligand, amine always comes before chloro because it starts with an A in alphabetical order. There's 5 of them. So this would be penta for the prefix 5, amine, and then chloro, cobalt, 3. So that is the name of the complex ion. Okay. And in that case, it still needs to be added on to the salt form, right? So like this is calcium chloride, despite the fact it has 2 Cl's, because you learned way back in 152, no prefixes. Same is true here. And so this is pentaamine chlorocobalt 3, and then leave a space, chloride for the salt. Okay, this first part looks like a run-on sentence. So there's no spaces within the complex ion. And then as I mentioned, this is alphabetical based on the name of the ligand. And then you will say how many there are with that. If you notice, the mono is not used on the chloro. Okay, so we don't put the mono in there. We just put that when it's 1, you just put whatever the name of the ligand is. Okay, and then lastly, just to mention, this Roman numeral is the charge on the metal ion. Okay, next one. There is something unusual that happens with our metals when they are in anions. So, for example, here, okay, in this case, let's take a look at this complex ion within this coordination compound. So in this case, this would be the equivalent, I'll put it over here, like potassium phosphate. So that's K plus and PO4 3 minus. So when you balance out the charges, you get K3 PO4. That's the same here. So this is K plus and COF6 3 minus. Okay, so take a minute. You can pause me and figure out what the charge is on the cobalt based on the ligand being fluoride ion. So if you did that, what you'd see is there's 6 negative ones. So that must mean that the charge on the cobalt is 3 plus, because 3 plus and 6 minus gives us a 3 minus. Now, in this case, this is an anion complex ion. And the naming will follow in the following way. This is still a potassium salt. So like this is potassium phosphate. So this would be potassium. No prefix to say that it is 3 of them. Just like we would not say tripotassium phosphate, right? We just say potassium phosphate. So this is potassium. And then now I'm going to do my thing. I have 6 fluoride ions, but we call that hexafluoro, because remember from the previous slide, that's the ending. Cobalt. And then here's the only weird part is that when they're in an anion, they go to ATE. So when they're an anion, they end in ATE ending. But I still now have to give the charge on that metal. So this one here is potassium hexafluoro cobaltate 3. Okay, so potassium hexafluoro cobaltate 3. Okay, so one last one, just to kind of be thorough on this. Let me give you one more. Okay, so take a minute. You can pause me and figure out what the charge is on the iron, what the charge is on the complex ion. And so pause me and figure that out, and then I'll go over that. Okay, so you're back, and you have then, again, there's potassium's plus. So this means that this is a 3 minus. Cn is Cn minus, which if you go back to the previous slides is cyanide, but we call it cyano for this. There's 6 of them at a -1, so that must mean that the iron is a 3 plus. So to name it, it'd be potassium. No prefixes on that. This is the equivalent, again, of like potassium phosphate, where we don't give a prefix for the 3 Ks. Potassium, hexa, cyano. And then here's the weird part that came up on the previous slide, that instead of calling it ironate, it gets switched to ferrate. And now we have to say that that has a charge of 3. And when do we do this? Again, is when the metal's in an anion, complex ion, negative ion. So there can be a lot to this, but again, since you're just going to identify these, students do well on this part. You have your notes in front of you, you have their names. So this is not such a, I guess you want to say, big deal in terms of being difficult. So try not to let it stress you out. Okay. So why are we doing this section? One of the most important parts of the chapter is in your book, 12, for this chapter, it's 12.6, which is called Crystal Fields Theory. And what you want to know about this part is that these transition metals have color and magnetic properties. And we can also use this section to really understand how a spectrophotometer works. So I think it's a good section to go through, and it's part of our learning objectives. Okay, so what we're looking at here is that many transition ionic compounds are highly colored, and they're also paramagnetic. Paramagnetic means that they'll have a slight attraction to a magnet. And maybe you went through this in Chem 200, but paramagnetic is the property that we see that has a slight attraction to a magnet or magnetic field. And then the idea is why, and it's things that are attracted to a magnetic field have unpaired electrons. Okay. So this is a nice little slide showing all the amazing colors that you can have with compounds of transition metals. They have a lot of interaction, and they interact in a different way with light. And so what we're going to talk about is what happens. And to do this, we have to understand why an object has color. So an object has color because it reflects the light of that color, or it absorbs light of the complementary color. And so we'll use what's called an artist's wheel to determine the complement of a color. So if you have a substance that appears to be green, so it looks green, that's because it's absorbed its complement of red. If you have a substance that looks violet, that means it's absorbed yellow. The other thing that's going to be important here is the idea to review your idea of wavelength and energy. So recall visible light is approximately 400 nanometers to 750 nanometers. The 400 nanometers, maybe I'll get fancy with my colors here. Yeah, why don't we do that? That'd be fun. See if I can get to it. Okay, so the 400 nanometers is purple or violet. So you see it over here, 400, right? The purple end is, if you recall from Chem 200, don't ever forget this, that the greater the wavelength, the smaller the frequency, the lower the energy. Let me put that up top because I don't want to put it right there. So recall from your Chem 200 material, that'll be important for your rest of your science lives, is the greater the wavelength, the smaller the frequency, the lower the energy. So then the opposite is true. The smaller the wavelength, the higher the frequency, the higher the energy. So the purple light compared to the red, the purple light has a shorter wavelength, so that is higher energy. Conversely, the red on this end of the spectrum is a longer wavelength, which will be a smaller energy. Okay, so again, for the compounds we're going to look at, and when we talk about a spectrophotometer, if an object absorbs light of a specific color, it's going to appear and it's going to transmit all the rest of them, and that's going to appear to us to be its complementary color. Okay, so this is showing that idea that if it absorbs violet, it's going to observed color will be its complement. So it's going to be greenish yellow. If it absorbs red, it's going to appear to be its complementary color. So let's go back. So if it absorbs red, it's going to appear to be green. If it absorbs violet, it's going to appear to be yellow. Okay. So this is just highlighting it more in a chart form. And let me take a look at something there. Oh, I see. Yeah, I think the part that was confusing was this green yellow. We would have just said yellow based on the chart. But it all depends, because I want to show you something that you see how if it were to absorb 400 nanometers, that's going to be on the yellow-green border. Okay, that's why it's written that way. All right. Okay. So we're going to explain why transition metals with their complex ions and these coordination compounds have color. And what it's going to have to do with, it's going to have to do with their d electrons. So recall that when we were looking at a complex like a cobalt-3, we just said that that was a D6. And let me double check that. Yes, so that was our D6. And so what you want to picture is that you have your d-orbitals. If you recall from Chem 200, there's 5 d-orbitals. And we're going to picture that they have an electron in them. So there's 6, 1, 2, 3, 4, 5, 6. Okay, so there's your cobalt 3. Now, if you have in an octahedral configuration, you're going to have 6 ligands coming in to that metal center. So here's a prettier picture of what I just tried to draw. Okay, now when those ligands come in, so you have the ligands that are going to come in to bond to the metal center. With some of the d-orbitals, there's a repulsion. Do you see how in this d-orbital and this d-orbital, do you remember those guys from Chem 200? If you notice, the ligand's going to interact directly with electrons in those orbitals. And what's that going to do is it's going to create some repulsion. So what's going to happen is that 2 of the orbitals are going to go up in energy. Then there's these 3 d orbitals here that when the ligand comes in, it misses a direct interaction with the d electrons. So those actually lower in energy. And we have a very famous then thing in chemistry, which is called crystal field splitting energy. And so the d orbitals get split, and there's this energy gap that's just given by a delta. This is called crystal field splitting energy. Now, what decides how big that gap is? The gap is determined by the metal center and also what the ligand is. So some complexes have a big gap. Some complexes have a small gap. Okay, so let's address that. There's some better pictures coming up. So here's my crystal field splitting energy given by that symbol. Okay, and so you have the 5 d orbitals, 3 go down, 2 go up. And this is for an octahedral arrangement. That's all you'll need to know. It's the octahedral one. Okay, so some ligands produce a small change. So this is what I would call a small energy gap. This one produces a large energy gap. And the ones that produce a small energy gap are called weak field ligands. The ones that produce a large energy gap are called strong field ligands. And this is where you're going to see then a distinction in color and magnetic properties. Okay, so water then in this example is shown as a weak field ligand, and cyanide or cyano is a strong field ligand. You see how the gap is much bigger, and that's going to affect its color and its magnetic property. Okay, so let's talk about the color. In this case here, this is, so let's see if we can name it. Why don't you take a second and pause and see if you can name this complex ion. So that would be hexa, aqua, titanium, three. Okay, why? Because this is neutral. So the titanium has to be the 3+. Take a minute and pause me and figure out what electron configuration titanium 3+ has. So you grab your periodic table and take a look. So regular titanium is argon 4s2, 3d2. If it loses 3, 4s is gone first in one of those, so it's a d1. So this explains why there's only one electron shown here. Okay, now you're going to put this into a spectrophotometer. And it has a crystal field splitting energy. That's a certain magnitude. You can picture that in this case, it's actually not showing a spec right now, but it's going to have options for all of these wavelengths in the visible range. Okay. What will happen is that it absorbs light that's within kind of that greenish yellow that promotes the electron to the higher d orbital. The rest of them are transmitted. And so what we would do was we go back to the color wheel. So it absorbs kind of on the green-yellow border. So let's go back to the color wheel. It absorbs here in the kind of greenish yellow range, which means that what's this going to look like? It's going to be a red-violet in terms of what color it appears. So let's go see if that's true. Yeah, so you see how it's a reddish violet color, okay? And that's all of them are, so all these wavelengths combined give us the appearance of the complementary color that we see. Okay, so now from a spectrophotometer point of view, when you put something into the spectrophotometer that's colored, in this case, the green light and yellow light that's absorbed is here in this wavelength. Okay, and that's what we would set the spectrophotometer to if we were analyzing this sample. Okay, so that sample would be colored and optimized for the light it absorbs. So looking at it the other way, which is that this is a reddish violet colored sample, then we know that the spectrophotometer would get set to its complementary greenish yellow wavelength to absorb that light. Okay, so the energy split that a compound has is the result of the metal ion and what its charge is and what ligand is attached to it. And so the colors will change depending on what ligand this is. So in this case, this is, for example, down here, chromium-3 in both of these. But do you see how with ammonia, it's one color, and with ammonia and chloride ion as its ligand, it's a different color. Here's vanadium 2+ in both of these, but vanadium 2+ here with water is this color, and vanadium 3+ is a different color. So the oxidation state causes a change in color, and then the ligand causes a change in color. Okay, so some ligands produce a very large, strong field, larger energy change, and some are weaker. So this is one that you would have, and I would say print this out or write out for your reference. So this would be a given. And I normally give it on a test, but you guys have your notes, so you can look at it with a prettier picture than I will give. So here, the stronger field ligands have a larger gap. The larger the gap, the shorter the wavelength of light absorbed. So let's think back then. Let's think back to what I wrote earlier. We have purple, violet, blue, green, yellow, orange, red. The violet end of the spectrum is high energy, shorter wavelength. The red is lower energy, longer wavelength. So strong field ligands with a larger energy splitting gap will absorb shorter lambdas, which would actually mean that they're going to absorb more on the purple. Down on this end are weaker field ligands, are smaller gaps. So maybe I'll write that in here, that for these strong field ligands, you have a big gap. For our smaller ones, our weaker field, a smaller gap. Okay, what this means, I'm going to get fancy with my colored pens, is on this end, these guys will absorb purple. So I actually, now that I'm going to get into this, I know I'm being kind of nerdy with my pens right now. It's okay, right? This guy would absorb purple. Okay, with the on this end with the weak field ligands, with a smaller crystal field splitting energy, those guys would most likely absorb red. And then what does this mean is if they remember what they absorb, their color is the complement of that. So let's go back. Try to click faster this time. Okay, if they absorb red, they're going to appear green, right? If they absorb red, they'll appear to us when we look at them to be green. And then if they absorb violet, purple, they're going to appear to be yellow. Okay, so let's go back. Put that in our slide there. I'm still clicking, sorry, kind of a little slow. Okay, so if they absorb purple, okay, they're going to appear to be yellow. So the substance will be yellow. I'll put, oh, you can't even see the yellow though. So that wasn't good. I was so excited to use that yellow. Okay, how about I do this? I'll keep it. I don't even think you can see that. Okay, I'll just go with a regular pen then. Okay, and then if it absorbs red, it's going to appear to be green. That I know will work. So what I really like you to consider then, you've worked with spectrophotometers at 152L. You may or may not have worked with them in 200 with the pandemic, but you will have seen them in, you work with them in 201L. So the idea is when you put your sample in there, it's going to be calibrated to absorb at a certain wavelength. That's the wavelength it's absorbing. And that's all based on the color it is. So we need the color to it, right? And then whatever it absorbs, it looks to us to be its complementary color. In the case of these transition metal complexes, some ligands produce a big gap, and those guys will absorb at more in the violet or purple range. Some create a small gap with those d-orbitals, and those absorb in the red region. Okay, we'll just finish by doing this problem. I think you can see the answer there, but that's okay. So all of these, when we're making that kind of comparison, will be usually the same charge of the metal. So these are all titanium 3+. We go to our spectrochemical series. Let me click back. So we're comparing, here's water as a ligand, ammonia, and cyanide. So water has the weaker field ligand, followed by ammonia, and then Cn minus strong field ligand. So if I were to write these out, the water has the smallest gap. Then the ammonia has a little bit bigger gap. And then the cyanide, Cn minus, has the largest gap. So this is our biggest crystal field gap compared to this one, compared to this one. Okay, and then who's more likely to absorb more towards the violet end would be this one, right? Because it's going to have the highest energy change, which would be the shortest wavelength for absorbing. So it would absorb more towards the violet end. And then over on this end with the smaller gap, it's more likely to absorb in red. Because that would be a lower energy, longer wavelength. Okay, one last thing. This will affect the magnetic property of the substance. So in this case, this is showing what happens to the magnetic property of manganese 2. So take a moment with your periodic table and double check what the number of electrons is for manganese 2. So manganese is argon 4s2, 3d, and count them over, 5. So if you're looking at manganese 2, loses the 4s first, this is a d5. So that's why it has, if you notice, 1, 2, 3, 4, 5 arrows. Now, if I go back, just not to confuse you, but just to show you, I didn't fill in, if I go back to this guy that I didn't fill in any electrons here. If you recall, titanium 3 on a previous slide that we did is a D1. So these guys would have 1 electron. So I think I like to make a big deal about that, because if you look at pictures in your book, they won't always have the same number of arrows or electrons, right? Because they are different in terms of their d electron number. Okay, something like water is a weaker field ligand than cyano. So you see how here, relative to cyano, it's weaker field. Smaller energy change than the cyano, that's strong field, and a higher energy change. So now let's picture, I know this has the final answer, but what I want to show you is I'm going to draw it like this. Too far, just a weaker field, so let me erase. Okay, so it's weaker field, not such a big gap. So now let's picture you're going to fill in these 5 electrons. Okay, the d-orbitals get split because of the ligand. And so look at what happens. You have 5 electrons. If the energy gap isn't so great, you can just fill them all in singly. So a weaker field ligand allows them to fill in singly, and then you end up with a whole bunch of unpaired electrons. And that's going to mean that it has paramagnetic properties. Okay, now Cn minus, on the other hand, is going to create a much bigger gap between those d orbitals that get split. And so when you fill in the 5, 1, 2, 3, 4, 5, they'd rather fill in the bottom level of D instead of singly because the energy gap's so much bigger. And so what will end up happening there is that you end up with not 5 unpaired electrons, but only 1. So its magnetic properties different and less. Its attraction to a magnetic field would be much less with just 1 unpaired versus 5. We call this idea, has some terminology. This one's called a high spin, this first one. High spin means that you can fill in like I did, 1, 2, 3, 4, 5, that they fill in singly. When they can't, because the energy gap's so great, that's called a low spin, where they're all starting to pair up down below. So a strong field ligand promotes a low spin complex. A weak field ligand promotes a high spin complex. Okay, here's another one. This is showing iron in 2 different complexes. So let's take a moment. This one here, water is neutral, so this iron must be 2 plus. This is 6 negative 1s. The whole thing's a 4 minus. So this is still a 2 plus, or comparing similar, right? Iron 2 plus, so let's go back. Iron regular is argon, 4s2, 3d, 1, 2, 3, 4, 5, 6. Okay, so that iron 2 plus is argon 3d6. So you see why there's 6 arrows. Okay, water, weak field ligand. Cyano, strong field ligand. So in the weak field, this energy gap's very small. So you can fill them like this. 1, 2, 3, 4, 5, and then you have no choice but to pair up. That creates a compound that's paramagnetic, unpaired electrons. In the case of a strong field ligand with a large energy gap, it does this. 1, 2, 3. Oh, I don't want to go up. Too high of energy. 4, 5, 6. And now you have all paired electrons. That's the diamagnetic. Paramagnetic with unpaired is attracted, slight attraction to a magnetic field. Diamagnetic is a repulsion to a magnetic field. And so this is a great example of a change in magnetic property based on the ligand that's attached to the metal.